Hey everyone, I'm back like 9 months later. Yeah, things have been kind of crazy and I ended up moving a lot of my content over to TikTok because it's TikTok, but I just wanted to check in and give you a little idea of how my research is going because it's going okay. It's going pretty well. And I had the chance to present a little bit about what I'm doing at the European Solar Physics meeting this morning. Unfortunately, because of Corona, it was not in Italy, but it was from my living room. But you know what? That's okay. It means I can make tea and sit on the couch and just relax during the whole thing. So if you have 7 minutes and are curious about what it's like being a PhD student in theoretical astrophysics, particularly in solar physics, then continue watching. Now keep in mind that this content is not geared at everybody. It's not necessarily geared at the public at large, but I think that it's something that can be understood more or less, even though it's geared towards solar physicists in the community. So if you don't understand anything, you probably shouldn't. Just leave it to me. But if you are curious anyway, enjoy it.
Hey everyone, I'm Becca and I'm working with Mats Carlson over at the University of Oslo, and we have been using simulations to try and understand solar atmospheric heating. If you'd like to get in touch with me at any point, my email will be on the screen the entire time, as well as this panel on the left hand with the QR code to our work and greater collaboration, which is wholesome. So as we all know, the coronal heating problem is still very much unsolved, but a cooperation of a lot of our work, I think, is beginning to nod towards a general solution to that problem. My little puzzle piece of that problem is the quiet sun. We feel very strongly that quiet sun fields are relevant contenders in terms of atmospheric heating on the sun, due to the fact that they are present on the face of the sun at all times and cover the majority of the sun. But since their fields are quite a bit weaker than active regions, the field topologies and stats are really, really difficult to nail down. So what we've done is we've manufactured a quiet sun simulation with our in-house model Bfrost in order to understand magnetic topologies that may lead to solar atmospheric heating. And so today I'm going to show you a case study for a magnetic feature that we've seen is associated with atmospheric heating in the simulation. Okay. So what we've done is we've set up a quiet sun simulation with a balanced vertical field at first and let it evolve for about 3 hours solar time. And at that time, we noticed that some interesting magnetic features were emerging in the rooted in the photosphere, but stretching into the chromosphere and lower corona. And what you see here in this vapor GIF over to the right is the Z component of the magnetic field at 3 different height slices, just so you can see a little bit about how that Z component of the field is evolving in time. This bottom boundary here, this is at 2.5 megameters beneath the solar surface. And as it was a balanced vertical field at first, it's just kind of salt and peppery at that lower boundary there. Okay. So what we noticed is that around that 3-hour solar time point, the magnetic feature that emerges is a plasma bubble. And that plasma bubble is associated with increases in bursts in atmospheric heating around those regions. Now, this figure here is a vertical slice through the simulation at y equals 7 megameters and stretching from about -2.5 to about 8 megameters in height. In MHD simulations, the current follows the magnetic field, right? So the current is a function of a changing or gradients in the magnetic field, not the other way around, because this is the MHD model. So that tells me that if I'm seeing total heating here, it is likely associated in the case of Joule heating with gradients in the magnetic field, which is a free parameter in Bfrost. And where I'm seeing viscous heating, that is associated with plasma shocks, in this case within the plasma bubble. This, though, is a plot of total heating. So it's the Joule heating plus the viscous heating normalized by density such that we can see these features emerging in the very tenuous solar atmosphere that we have. Okay. So as the goal was to understand the types of magnetic topologies that lead to these types of heating, I wanted to trace those field lines in a way that made sense. So fortunately for me, we have collaborators over in Stockholm who have developed a module for Bifrost called Corks. And what Corks basically is a test particle module that allows us to kind of throw test particles into each voxel of the simulation, and they will follow the magnetic and velocity fields as the simulation evolves. So I went ahead and did a rerun of the simulation with Quarks activated. And it basically just saves me the hassle of having to add back to the magnetic field myself with the velocity field. And I could follow the evolution of the topology as the bubble wiggles around and collapses. So what you're seeing on the right-hand side GIF is a visualization with vapor again, where I have selected some of those quarks and had traced the magnetic field lines that are associated with those quarks as the simulation goes on, as that loop wiggles around and collapses. And an interesting thing here that we see is that as the bubble collapses, it's not a total collapse into no feature at all, right? At the beginning, as we see in the beginning of this GIF, we have a very nice loop. But at the end of the GIF, we still have a loop. It's just not the same orientation. This simulation is periodic in X and Y. So what you see at the end of this collapse is actually just a change in connectivity across the boundary. This is still a loop, but it's like two halves of a loop across the boundary, which is a very interesting result, I think. So looking ahead to what's next in the analysis phase, because this is very much still a work in progress, we have identified the feature. We do know that it is associated with heating, but why does that bubble collapse? Why does the connectivity change? I'm suspicious that it's more of a boundary condition issue than anything, but it's an important thing to investigate as well. What are the stats on the magnetic feature itself, as well as different layers in the atmosphere and the photosphere? I've been running stats along the flow lines. I've also been running stats at heights in the solar photosphere and atmosphere where we are also likely to have observations, right? Because the goal is to really be able to coexist with observations and simulations, where the observations can inform the simulations, but the simulations should be complementing the observations. And so what I've done is I've run some synthetic spectra for iron 1 at 630 that would give me a magnetogram comparable to magnetogram observations. Although I'm suspicious that I might need to run synthetic spectra for a chromospheric line instead, possibly compared to iris observations, because it's likely here that the source of heating is probably chromospheric current sheets. But again, that needs to be explored by me. And finally, how does this heating impact the atmosphere at large? So to finish up, I'll just leave you with the big version of my poster. Again, my email is here. Feel free to get in touch.
So that is a sample of what I've been working on lately. And I have a few more exciting things coming up, but research-wise, this is what I got to present today at the Solar Physics meeting. As always, if you guys have any questions about my job or what I do, feel free to ask me. Otherwise, I hope you have a really great day. Bye.